Among the countless galaxies scattered across the cosmos, stretching into billions upon billions, astronomers have discovered nearly every shape and size imaginable: spirals, ellipticals, irregulars, and exotic cosmic oddities. Yet hidden among this ocean of starlight lies something profoundly rare, a class of galaxies so strange that they almost seem out of place in the modern universe. They are dazzlingly bright, strikingly green, and astonishingly few in number. These are the Green Pea Galaxies, celestial peas in the endless cosmic pod. Their discovery changed how astronomers view galactic evolution, and their rarity makes them some of the most intriguing objects ever observed. These tiny green jewels of the universe hold secrets about the earliest galaxies, the formation of stars, and even the dawn of cosmic light itself. They remind us that the universe still has surprises, even in the most unexpected forms. When astronomers first began to study the strange objects that would later be known as Green Pea Galaxies, what stood out immediately was how utterly different they were from the galaxies we usually imagine when we think of the cosmos. The Milky Way, for example, is vast and structured, containing hundreds of billions of stars spread across its majestic spiral arms. Green Pea Galaxies are nothing like this. They are small, often barely 1/10 the size of our galaxy, yet they radiate an extraordinary glow. To the eye of a telescope, they appear as tiny, round, greenish dots, compact in structure and lacking the sweeping arms or organized disks of larger galaxies. Despite their miniature scale, they burn with an intensity that defies their size, shining brightly in the night sky, not because of their immense star population, but because of what is happening inside them. These galaxies are bursting with life on a cosmic scale. They are cradles of furious star formation, producing new stars at rates far higher than most galaxies around them. Their appearance is perhaps their most defining feature. Unlike the soft glows of spiral galaxies or the fuzzy shapes of irregular ones, Green Pea Galaxies are marked by a striking, almost neon green hue when captured by telescopes that use specific filters. This glow comes not from the stars themselves, but from the gas that surrounds them, particularly the ionized oxygen that emits light in a very specific green wavelength. This means that what we are seeing is not simply starlight, but the brilliant chemical fingerprint of gas excited by some of the most powerful and energetic processes in the universe. This unique coloring is what makes these galaxies stand out against the deep background of space, and what first led observers to notice that they were unlike anything else in the cosmic catalogue. It's important to understand that these galaxies are compact in more than just their size. They are dense, crowded, and tightly packed with energy. Where most galaxies spread their stars across vast distances, Green Pea Galaxies concentrate their stellar nurseries into small regions, creating environments where massive stars are born in rapid succession. This high density of young stars contributes heavily to the light we see, because young, hot stars emit extreme amounts of ultraviolet radiation. That radiation ionizes the gas around them, stripping electrons from atoms, and as those electrons recombine, the gas glows. In the case of Green Pea Galaxies, the glow happens to be dominated by oxygen, giving rise to the now iconic green coloration. What also sets them apart is their scarcity. In the modern universe, galaxies that look like this are not common at all. Most galaxies, including ours, have long since matured past the stage of rapid star formation and instead exist in a slower, more stable state of evolution. Green Pea Galaxies, by contrast, look like they've been frozen in time, behaving more like the primitive galaxies that existed just a few billion years after the Big Bang. In many ways, they are relics, cosmic fossils still burning with the same fire that once shaped the earliest galaxies. Their discovery in the contemporary universe was unexpected, precisely because scientists believed such galaxies should no longer exist. Their presence in our cosmic neighborhood, relatively close by on intergalactic scales, gives astronomers a chance to study galactic youth without having to peer across the immense distances of space and time that normally separate us from the earliest galaxies. Because of their rarity and their peculiar light, Green Pea Galaxies have become laboratories for exploring some of the most important questions in cosmology. They are small, yet they are mighty in their contribution to science. Their compact size allows astronomers to observe starburst activity in a more concentrated environment, making them perfect for testing models of star formation. And since they resemble galaxies from the early universe, they serve as stand-ins for those ancient systems, allowing us to learn about cosmic history without having to rely only on the faintest signals from galaxies billions of light years away. To put their scale into perspective, while the Milky Way stretches across about 100,000 light years and contains over 200 billion stars, Green Pea galaxies are often just a few thousand light years wide and contain only a few billion stars at most. Yet in terms of brightness, they punch far above their weight. Their luminosity can rival or even exceed galaxies far larger than themselves because of the incredible intensity of their ongoing stellar creation. In essence, they are small cosmic engines running at full throttle, burning fuel and forging stars at rates disproportionate to their size. This imbalance is part of what makes them so compelling. They show that size isn't everything in the universe, and that even small galaxies can leave a huge imprint on cosmic evolution. Their strange glow, compact structure, and rare presence all come together to make Green Pea Galaxies unlike anything else in astronomy. They are neither ordinary star-forming galaxies nor fully evolved systems, but rather a unique class that stands out both visually and scientifically. They bridge the gap between the galaxies of the distant past and the galaxies of the present day, giving us a unique perspective on how cosmic structures can vary and evolve. To scientists, they are a gift, rare enough to be fascinating, nearby enough to be studied in detail, and powerful enough to shed light, literally and figuratively, on some of the universe's greatest mysteries. The story of how Green Pea Galaxies came to light is as extraordinary as the galaxies themselves, because their discovery wasn't the result of a grand scientific expedition armed with massive telescopes and complex algorithms. Instead, it was the outcome of an ambitious citizen science project known as Galaxy Zoo. Launched in 2007, Galaxy Zoo was designed to enlist the help of ordinary people, anyone with an internet connection, to classify galaxies using images taken from the Sloan Digital Sky Survey. Millions of galaxies were photographed in unprecedented detail, far too many for a small team of astronomers to sort through alone. So, the project opened the doors to volunteers, asking them to help distinguish spirals from ellipticals, irregulars from mergers, and in doing so, contribute directly to science. It was a simple yet brilliant idea. Crowdsource the vast and complex work of categorizing the universe. Amid the countless volunteers who poured their time into the project, a group of amateur astronomers began noticing something unusual. While most galaxies they classified fit into neat categories, some of them stood out, tiny, round, and glowing an odd shade of green. These objects didn't resemble the sweeping spiral arms of grand design galaxies, nor the faint smudges of distant ellipticals. They looked like glowing peas scattered across the cosmic field. At first, these green dots were dismissed as curiosities, perhaps just artifacts of the imaging process or odd statistical flukes. But as more and more participants reported them, it became clear that something unusual was going on. The amateurs weren't simply misclassifying galaxies, they were stumbling onto an entirely new class of object that astronomers had overlooked. The pivotal moment came when the Galaxy Zoo Forum community gave them a name. Volunteers affectionately dubbed the objects Green Peas, inspired by their round shape and striking coloration in the telescope images. What began as a quirky nickname soon stuck, and before long, professional astronomers themselves adopted the term. This grassroots christening of a new galactic type demonstrated the power of collaboration between scientists and the public. What could have been brushed off as insignificant noise was instead recognized as a profound cosmic discovery. Once these galaxies were flagged, professional astronomers turned their attention to them with renewed curiosity. Detailed spectroscopic studies revealed that these weren't glitches or misidentified objects at all. They were real galaxies, compact and energetic, with characteristics unlike almost anything else in the modern universe. The green glow, scientists discovered, came from ionized oxygen, excited by intense star formation. A clear sign that these galaxies were small but incredibly active. The initial skepticism gave way to excitement as researchers realized that Galaxy Zoo's volunteers had uncovered something genuinely rare. The serendipity of this discovery cannot be overstated. For decades, professional astronomers had been scanning the skies with the most advanced instruments available, yet these galaxies had slipped under the radar. Their small size and unusual properties meant they didn't stand out in traditional surveys, and it took the keen eyes of thousands of non-experts to draw attention to them. In many ways, Green Pea Galaxies are a perfect example of how science sometimes advances not through carefully planned steps, but through unexpected twists of chance. A global community of volunteers, motivated by curiosity and wonder, managed to spot the cosmic oddballs hiding among billions of galaxies. What's remarkable is how quickly the scientific community embraced this accidental discovery. Instead of brushing it aside, astronomers recognized the significance of what had been found and dove deeper into their investigation. Papers were published, follow-up observations were made, and soon Green Pea Galaxies were not only accepted but celebrated as a major addition to our understanding of galactic diversity. This was a turning point for citizen science in astronomy, proving that ordinary people could play an essential role in groundbreaking discoveries. It wasn't just about lending a hand with busy work, it was about expanding the very boundaries of what we know. The accidental nature of this finding adds to the mystique of Green Pea Galaxies. If it weren't for the Galaxy Zoo project, it's possible they might have gone unnoticed for many more years. Their discovery in 2007 is a reminder that the universe still has surprises in store, and that those surprises can sometimes be revealed by the most unexpected observers. It also shows that science is not reserved for a select few, but can be a collective endeavor, where curiosity, persistence, and sharp eyes can open entirely new windows into the cosmos. The story of the Green Peas is, therefore, not just about rare galaxies. It is about how chance, collaboration, and human curiosity can converge to change the way we see the universe. When the amateur astronomers of Galaxy Zoo first stumbled upon these unusual galaxies, one of the first things they noticed was how different they looked from the thousands of other cosmic objects they were classifying. Most galaxies in the Sloan Digital Sky Survey appeared as faint smears of light, elongated spirals, or hazy elliptical shapes. These, however, were something else entirely: small, perfectly round, and strikingly green against the backdrop of space. Their shape and color immediately stood out, and it was this combination that inspired the nickname that would stick with them forever: Green Peas. The name wasn't chosen by scientists in a laboratory or committee. It emerged naturally from the discussions among Galaxy Zoo volunteers. As people shared their observations on the project's online forums, they kept pointing out the odd little green circles that looked nothing like the galaxies they were used to seeing. Their resemblance to tiny peas, scattered across a field of stars, made the name almost inevitable. The greenish hue in particular made them feel playful and approachable, so much so that a discovery of enormous scientific importance was given a name you might expect from a backyard garden rather than a cosmic observatory. But the nickname captured their essence perfectly, and it quickly became the shorthand not only among volunteers, but also in professional astronomy circles. What started as a quirky inside joke among citizen scientists soon became the official label for one of the rarest galaxy types in the universe. Their pea-like appearance is due to their extreme compactness. Unlike sprawling spiral galaxies that stretch across hundreds of thousands of light-years, Green Pea Galaxies are incredibly small, typically spanning only a few thousand light-years at most. To the telescopes of the Sloan Digital Sky Survey, they appeared as little round blobs of light, almost like green marbles against the cosmic canvas. This compact, spherical shape, so uniform and distinct, made them instantly recognizable compared to the irregular or diffuse shapes of other small galaxies. To the human eye, scanning image after image, their pea-like nature made them impossible to miss. The green color is where things get even more interesting. Astronomical images from surveys like Sloan often use filters to capture specific wavelengths of light. In the case of the green peas, their strongest emission came from highly ionized oxygen gas. This gas, when hit with intense ultraviolet light from the hot young stars inside the galaxy, glows at a very particular wavelength. When that wavelength is mapped to visible color in the survey images, it appears green. So what looks like a quirky vegetable-colored galaxy is in fact the visible fingerprint of powerful astrophysical processes, rapid star formation heating gas to extreme levels, causing oxygen atoms to light up like cosmic neon signs. The choice of name is also a perfect example of how astronomy balances scientific precision with human imagination. On one hand, these galaxies could have been given a technical, sterile label, something along the lines of compact emission line galaxies or starburst dwarfs with O3 emission. And in fact, in academic papers, they are sometimes described this way. But names like that rarely capture the public's attention. Green Pea Galaxies, by contrast, is both accurate in describing their appearance and memorable enough to stick in people's minds. It bridges the gap between rigorous science and the playful curiosity that drives discovery, making these galaxies not only a subject of research, but also a symbol of how science can be fun and accessible. The name also reflects something deeper about the discovery itself. Because they were first identified not by professionals, but by volunteers, ordinary people fascinated by the cosmos, the name Green Peas has a grassroots authenticity. It wasn't imposed from above, it was born out of collective wonder. That's part of why the name endured. It carries with it the story of how these galaxies were found, of people poring over images late at night, marveling at their odd little glow, and giving them a name that felt natural. Every time astronomers refer to Green Pea Galaxies, they are invoking that history of collaboration between the scientific community and the public. What's fascinating is that even though the name might sound whimsical, it has become the official term used in research papers, lectures, and conferences. It is not unusual now to hear astrophysicists, people dealing with the most complex models of galaxy evolution and cosmic history, talk seriously about green peas. The nickname has transcended its playful origins and become a permanent part of scientific vocabulary, reminding us that sometimes science advances with a smile. And in a way, the name perfectly reflects the galaxies themselves: small, bright, surprising, and impossible to ignore. At first glance, it might be tempting to dismiss Green Pea Galaxies as insignificant because of their size. Compared to giants like the Milky Way, they are minuscule, often only a few thousand light-years across, while our own galaxy spans around 100,000 light-years. In terms of stellar population, they are just a fraction of the Milky Way's mass, with only a few billion stars compared to our galaxy's hundreds of billions. By nearly every measure of scale, diameter, star count, or overall mass, Green Pea galaxies appear tiny, almost like cosmic minnows swimming among galactic whales. Yet, despite this apparent smallness, they defy expectations by shining with a brilliance that rivals galaxies many times their size. Their compactness seems to amplify their light, turning them into some of the most dazzling star-forming engines in the nearby universe. The key to their power lies in what is happening inside them. Green Pea galaxies are not calm, stable collections of stars like the Milky Way, where most stars are long-lived and star formation proceeds at a modest pace. Instead, they are boiling cauldrons of energy, with furious bursts of star formation happening at rates out of proportion with their size. In some Green Pea galaxies, new stars are being created up to 10 times faster than in galaxies much larger than themselves. Imagine a small town producing the same amount of energy as a bustling metropolis. That's essentially what Green Pea galaxies are doing on a cosmic scale. This relentless production of stars floods their galaxies with ultraviolet light, ionizing the gas around them and creating the brilliant green glow that makes them stand out in images. Their unusual brightness is not just a quirk of their color, but a real indication of their extreme activity. Starburst regions within these galaxies are dominated by massive young stars, the kind that shine fiercely but live only short lives. These stars are incredibly hot and pour out radiation that excites surrounding gas clouds, making the entire galaxy shine like a beacon. Because of this, a Green Pea galaxy, despite its tiny size, can often outshine galaxies with far more stars. This is why astronomers describe them as mighty. Their output and impact on their surroundings are magnified far beyond what their small stature would suggest. Another way to think about their strength is to consider energy density. Large galaxies like the Milky Way spread their stars across vast regions, so their brightness is distributed over enormous distances. Green Pea galaxies, however, pack their stars into a much smaller volume. That concentration means that light, radiation, and energetic processes are crammed into a compact space, intensifying the effects. If you were to stand hypothetically within a Green Pea galaxy, the night sky would be ablaze with nearby bright stars, nebulae, and glowing regions of ionized gas. The sheer density of star-forming regions would make it an environment unlike anything we could imagine from our relatively quiet galactic home. This small but mighty nature is also what makes them such valuable subjects for astronomers. Their extreme starburst activity allows scientists to study the processes of star formation in detail. It's like observing galaxy evolution under a magnifying glass, where everything happens more quickly and more intensely. Instead of spreading star creation over billions of years, Green Pea galaxies seem to compress those events into shorter, more violent bursts. That makes them snapshots of a crucial stage of galactic growth, providing insights into how galaxies ignite and evolve. It's worth noting that their apparent contradiction, tiny yet powerful, echoes what astronomers see in the earliest galaxies in the universe. When the first galaxies formed, they too were small, compact, and disproportionately bright, fueled by rapid star formation in a pristine cosmic environment. Green Pea galaxies resemble these ancient systems, making them living analogues of what the universe looked like more than 13 billion years ago. In that sense, their small size isn't a weakness, but rather a signature of their unique role in cosmic history. What makes them even more fascinating is how their size affects their evolutionary path. Larger galaxies tend to stabilize over time, with their immense gravity and diverse structures spreading out the processes of star birth and death. Green Pea galaxies, with far less mass and structure, live in a state of constant volatility. Their bursts of star formation are so intense that they may blow away gas, preventing future stars from forming. This precarious balance between growth and self-destruction means that their brilliance may be temporary, a short but spectacular phase in a galaxy's life. Their rarity in the modern universe may reflect the fact that such galaxies burn brightly but fade quickly, leaving behind only a handful for us to find today. To see a galaxy so small shine so fiercely challenges our intuition about the cosmos. It reminds us that size does not dictate importance, and that some of the most impactful processes in the universe can happen in the unlikeliest of places. Green Pea galaxies embody this paradox. Diminutive in scale, yet mighty in power, their very existence defies expectations and forces astronomers to rethink what galaxies can be. They may be peas by appearance, but their cosmic impact is anything but small. The most striking feature of Green Pea galaxies, the thing that sets them apart at first glance, is their unmistakable green glow. While most galaxies show up as bluish spirals, reddish ellipses, or faint smudges of white in survey images, the peas practically scream for attention with their bright, neon-like green coloration. This unusual hue is not a trick of photography, nor is it simply an artistic filter. It is the direct result of the physics happening inside these galaxies, where furious star formation and the chemistry of interstellar gas combine to create one of the most distinct visual signatures in the cosmos. At the heart of this glow lies oxygen, one of the most abundant elements in the universe after hydrogen and helium. In normal galaxies, oxygen exists in clouds of gas, but in Green Pea galaxies, those clouds are hit by torrents of radiation from newly formed massive stars. These stars are blazing hot, emitting ultraviolet light powerful enough to strip electrons from the atoms in the surrounding gas. When an oxygen atom loses multiple electrons, it becomes what scientists call highly ionized. In this state, the atom is unstable and constantly trying to return to balance by recapturing electrons. When the electrons fall back into place, energy is released in the form of light at very specific wavelengths. For oxygen, one of the strongest of these emissions falls right in the green part of the visible spectrum. In astronomical terms, this emission is often referred to as the O3 line, shorthand for doubly ionized oxygen. When telescopes equipped with filters look at galaxies in different wavelengths, Green Pea galaxies light up with this distinct green emission line, while other galaxies remain dominated by different colors, depending on their star populations and gas. What makes the peas special is not just that they emit green light, but that they do so overwhelmingly. Their environments are so dominated by massive, young stars, and so rich in gas, that the oxygen emission becomes the most prominent feature. This gives them their pea-like coloration in Sloan digital sky survey images and makes them immediately recognizable among millions of other galaxies. It's important to note that the green we see is not literally what human eyes would perceive if we looked through a telescope ourselves. In reality, our eyes are not sensitive enough to pick up faint colors from distant galaxies. Instead, the Sloan Digital Sky Survey and similar projects use filters that isolate specific wavelengths of light, then assign colors to them for composite images. The green hue of the peas comes from the filter that captures the O3 emission, mapped into the green channel of the image. This isn't a fabrication, it's a scientifically accurate representation of what wavelength is strongest, but it does mean the color is emphasized in ways our naked eyes would miss. In a sense, the green is a code telling astronomers about the physical processes at work in these galaxies. The intensity of this glow also reveals something about the conditions inside the galaxies. For oxygen to become so strongly ionized, the radiation field must be extreme, which in turn means that the stars powering it are unusually hot and young. These stars are often massive, perhaps dozens of times the mass of the Sun, burning through their fuel rapidly and living short, violent lives. Their ultraviolet output not only ionizes gas, but also influences how the galaxy evolves, shaping winds, carving cavities in gas clouds, and triggering further star formation in surrounding regions. In this way, the green glow is both a signature and a symptom of a deeper process, a galaxy in the throes of a starburst, where creation and destruction play out in cosmic cycles. This glow also ties Green Pea Galaxies to one of the great mysteries of the universe's early history, the era of cosmic reionization. Billions of years ago, after the Big Bang, the universe entered a dark age when neutral hydrogen filled space and absorbed light, preventing it from traveling freely. At some point, ultraviolet radiation from the first galaxies and stars reionized this hydrogen, clearing the fog and allowing the universe to become transparent. Astronomers suspect galaxies similar to the green peas were responsible for this transformation. The intense ultraviolet light that ionizes oxygen in these galaxies today could be an echo of what early galaxies did on a much larger scale, reionizing hydrogen across the cosmos and ending the Dark Ages. In this way, the green glow is not just an oddity, it is a clue to one of the most transformative events in cosmic history. What makes this even more fascinating is how rare it is in the modern universe. Most galaxies today are older, more chemically enriched, and calmer, with star formation slowed to a steady pace. Their gas no longer glows so intensely, and their light is dominated by older stars. Green Pea Galaxies, by contrast, are like cosmic throwbacks, pockets of youthful fury in an otherwise mature universe. Their green glow is a flare that tells astronomers, here lies a galaxy caught in an unusual state, shining with the kind of energy that once lit up the cosmos billions of years ago. So while the nickname Green Peas might sound whimsical, the glow that inspired it is anything but trivial. It's the visible signature of powerful astrophysics at work. Hot young stars, ionized oxygen, and violent bursts of star formation, all crammed into tiny galactic engines. That eerie green light is a window into processes both ancient and ongoing, a signal that these galaxies are not only rare, but also immensely important in understanding how the universe came to shine. One of the most astonishing features of Green Pea Galaxies is the sheer pace at which they churn out stars. In most galaxies, star formation is a relatively steady process. New stars are born, but at rates that are balanced against the available supply of gas and the galaxy's overall stability. The Milky Way, for instance, produces roughly 1 or 2 new stars per year, a modest pace that has kept it evolving for billions of years without exhausting its gas supply. Green Pea Galaxies, however, defy this quiet rhythm. Despite being far smaller than the Milky Way, many of them form stars at rates up to 10 times higher. This means that in proportion to their size, they are among the most efficient star factories in the entire universe. This phenomenon is what astronomers call a starburst, a period of explosive star formation where the usual balance of galactic life is thrown into overdrive. Starbursts are rare and usually triggered by dramatic events like galaxy collisions or intense inflows of gas. In the case of Green Pea Galaxies, the reasons are still being studied, but the evidence is clear. These tiny galaxies are undergoing a phase of rapid creation, pumping out stars far faster than most galaxies in the nearby universe. The result is a dazzling compact system where hot, young, massive stars dominate the light output, flooding the surrounding gas with radiation and giving rise to the galaxy's distinctive glow. The efficiency of their star formation is extraordinary. While larger galaxies spread their star-forming regions across vast disks or spiral arms, Green Pea Galaxies concentrate their activity into small, dense pockets. This means that within a space only a fraction of the Milky Way's size, they are producing comparable or even greater amounts of light. Imagine a small workshop somehow outproducing a massive industrial factory. This is the scale of imbalance at play. The density of massive stars in these galaxies creates environments that are not only intensely bright but also highly energetic, with shockwaves, stellar winds, and supernova explosions shaping the entire galaxy in relatively short timescales. The consequence of such rapid star formation is that these galaxies burn through their fuel much more quickly than typical galaxies. The gas reservoirs that fuel star birth are finite, and Green Pea Galaxies are consuming theirs at breakneck speed. If they continue at this pace, they risk exhausting their supplies of hydrogen and helium in a fraction of the time it takes larger galaxies to do so. This suggests that their current brilliance may represent only a brief stage in their lives, a cosmic flare-up that will eventually fade, leaving behind a quieter, more stable remnant galaxy. In this way, Green Pea Galaxies are like fireworks, small, compact, but spectacular in their burst of activity, shining fiercely before eventually dimming. Their starburst behavior also explains some of their unusual chemical properties. Because they are producing stars so rapidly, many of those stars are massive and short-lived. These massive stars quickly explode as supernovae, enriching the galaxy with new elements, but also driving out large amounts of gas through powerful winds. This feedback process both sustains and limits star formation, creating a cycle of intense growth followed by self-regulation. The balance is precarious, and it is part of why Green Pea Galaxies are so rare today. Most galaxies long ago passed through their starburst phases and settled into quieter states. But the peas seem to have been caught in the act, still burning through their reserves at extraordinary rates. Astronomers study this furious activity not only because it is fascinating in its own right, but also because it provides clues about the early universe. Billions of years ago, during the first epochs of galaxy formation, starburst activity was far more common. Galaxies were smaller, gas was abundant, and collisions happened frequently, all of which triggered rapid star formation. Green Pea Galaxies are echoes of this ancient time, living examples of how galaxies behaved in the young cosmos. By observing their starbursts, scientists can piece together how the earliest galaxies built up their stellar populations, how they influenced their environments, and how they contributed to major cosmic events like reionization. What makes them even more compelling is that these starbursts happen in galaxies that are so small compared to the giants we usually study. Because of their limited size, the effects of rapid star formation are amplified and easier to measure. Astronomers can observe how stellar winds carve bubbles in the interstellar medium, how radiation leaks out into intergalactic space, and how quickly elements like oxygen and carbon are produced. Each Green Pea Galaxy becomes a natural laboratory where the physics of star formation is put under extreme conditions, allowing scientists to test models and refine theories about how galaxies grow and evolve. Ultimately, their reputation as extreme star formation factories is what makes Green Pea Galaxies so important in modern astronomy. They are compact furnaces burning at maximum capacity, showing us what galaxies can do when conditions align for explosive growth. Their existence challenges the idea that small galaxies must always be faint and unremarkable. Instead, these cosmic peas prove that even the tiniest of galaxies can shine with the intensity of giants, reshaping our understanding of how the universe builds its stars. Green Pea galaxies are more than just astronomical curiosities. They are time capsules of cosmic history. To look at them is to glimpse what the universe itself might have looked like over 13 billion years ago, when the very first galaxies were just beginning to take shape. Unlike the Milky Way or other massive galaxies that have evolved and matured over billions of years, Green Pea galaxies are astonishingly primitive. They possess low metallicity, meaning they contain far fewer heavy elements like carbon, oxygen, and iron compared to galaxies like our own. In astronomy, metals are created through generations of star formation and supernova explosions, so the lack of these elements suggests that Green Pea galaxies haven't had much time to evolve. In other words, they are chemically young, frozen in a state that strongly resembles the earliest galaxies ever born. This youthfulness is what makes them so valuable. Billions of years ago, after the Big Bang, the universe contained only hydrogen, helium, and tiny traces of lithium. The first galaxies formed out of this pristine gas, and their stars began forging the heavier elements through nuclear fusion. But because those galaxies are so far away, studying them directly is incredibly difficult. Their light has traveled for over 13 billion years, stretched and dimmed by the expansion of the universe, making them faint and elusive, even for our most powerful telescopes. Green Pea galaxies, however, offer an accessible alternative. They are nearby, close enough to be studied in great detail, yet they display the same characteristics as those primordial galaxies. It's as if nature has handed us a sample of the early universe preserved within reach. What is especially striking is how compact and intense they are, much like the very first galactic structures that emerged from primordial clouds of gas. In the early universe, galaxies were far smaller than they are today, tiny clumps of stars and gas merging together to eventually form giants like the Milky Way. Green Pea galaxies mirror this phase of galactic infancy, showing us how these early systems might have appeared before they grew larger through mergers and accretion. Their starburst activity is also a clue. The first galaxies are thought to have undergone intense bursts of star formation, lighting up the cosmos and playing a crucial role in transforming it from a dark, neutral state into one that was transparent and filled with light. By observing Green Pea galaxies, scientists can witness that very process unfolding in a local context. Their resemblance to early galaxies is further reinforced by the fact that many green peas leak ionizing radiation into intergalactic space. This is one of the hallmarks of the so-called epoch of reionization, a period roughly 13 billion years ago when the first galaxies emitted powerful radiation that stripped electrons from hydrogen atoms, making the universe transparent to light. Understanding how this transition occurred is one of the biggest questions in cosmology, and Green Pea galaxies may hold the answers. Their porous, turbulent structures, carved by supernovae and stellar winds, allow radiation to escape much as it did in the early universe. This means that in studying them, astronomers may be uncovering the very mechanisms that ended the cosmic dark ages. What makes this even more compelling is the paradox they embody. Green Pea galaxies exist in the modern universe billions of years after the first galaxies formed, and yet they retain these primordial qualities. How is it that such galaxies survived, unaltered, while most of the universe moved on to greater complexity and maturity? One possibility is that Green Pea galaxies are products of special environments, isolated regions of the cosmos where conditions prevented them from merging into larger systems. Another theory is that they are rejuvenated galaxies, somehow reset into a youthful state by massive inflows of pristine gas. Whatever the explanation, their existence provides a rare opportunity to see cosmic infancy preserved in the present. It's not an exaggeration to say that Green Pea Galaxies are living fossils of the universe's earliest days. Just as paleontologists study ancient bones to reconstruct the story of life on Earth, astronomers study these galaxies to reconstruct the story of cosmic dawn. Every spectrum taken, every detail observed, is a piece of a larger puzzle that connects us directly to the birth of galaxies themselves. They embody a kind of cosmic paradox, ancient in what they reveal, yet young in their chemical and structural simplicity. They are windows into the past, letting us study in detail what would otherwise remain hidden behind billions of light years of distance. And perhaps the most humbling thought is this: when we gaze at a green pea galaxy through a telescope, we are not just looking at a strange green glow in the night sky. We are looking at a mirror of the very first cosmic structures, a reminder of how the universe began its grand story of building stars, galaxies, and ultimately the conditions for life itself. In these tiny luminous orbs, the universe has preserved echoes of its own childhood, frozen in time for us to discover. Looking at green pea galaxies is like holding a magnifying glass up to the ancient pages of the universe's history book. They offer something astronomers crave: a chance to study in detail what galaxies may have been like billions of years ago, without the overwhelming challenge of observing across vast cosmic distances. Normally, if we want to peer back into the early universe, we need to use telescopes powerful enough to catch the faint, red-shifted light of galaxies that existed over 13 billion years ago. These galaxies are incredibly dim, distorted by distance, and often beyond the reach of even our most advanced instruments. But green pea galaxies are a rare exception to this rule. They are nearby in astronomical terms, some only a few billion light-years away, yet they look and behave almost exactly like the primitive galaxies of the cosmic dawn. This strange overlap of time makes them natural laboratories. Instead of struggling to capture faint smudges of ancient light, astronomers can study green peas in much higher resolution, dissecting their properties with powerful instruments like the Hubble Space Telescope or ground-based observatories. By analyzing their spectra, scientists learn about their chemical composition, star formation rates, radiation leakage, and the temperatures of their interstellar gas. Every one of these details is a clue that reconstructs what galaxies looked like in their infancy. In a sense, green peas collapse billions of years of cosmic history into a single, present-day snapshot that we can examine up close. What makes them particularly valuable is their resemblance to galaxies from the epoch of reionization, when the first galaxies were just beginning to shape the universe. During that time, galaxies were compact, low in heavy elements, and dominated by bursts of star formation, the very same traits we see in green peas today. By studying how they generate and release ionizing radiation, astronomers can model how the first galaxies contributed to the great transformation of the universe from a dark, opaque place to the transparent, light-filled cosmos we live in now. Without green pea galaxies, we would be left piecing together fragments of theory and distant, nearly invisible galaxies. With them, the picture becomes sharper and far more tangible. Their utility extends beyond the cosmic reionization era as well. They also help scientists understand the evolutionary pathways galaxies can take. Not all galaxies follow the neat pattern of steady growth and enrichment over billions of years. Some remain locked in a state of arrested development, while others flare up in starburst phases that echo conditions from the universe's earliest times. Green peas demonstrate that the early universe template didn't disappear completely. It can still emerge in rare circumstances, even in a cosmos 13.8 billion years old. This allows astronomers to compare how galaxies evolve under different conditions, and to identify the critical factors that determine whether a galaxy will form or not, galaxy becomes a sprawling spiral like the Milky Way, or remains a small, turbulent starburst system. The implications stretch even further, because these galaxies give us a baseline for interpreting the data coming from next-generation observatories like the James Webb Space Telescope. Webb is already revealing thousands of galaxies from the universe's first billion years, but interpreting what those blurry, ancient smudges represent requires context. Green Pea Galaxies provide exactly that context. They are analogues we can study in fine detail and then apply to understanding what Webb sees at the edge of the observable universe. In a way, green peas serve as Rosetta Stones for early galaxy research, translating faint signals from the distant past into a language astronomers can actually understand. Perhaps the most remarkable aspect of studying green pea galaxies as windows into the past is the philosophical perspective they provide. When we examine their blazing starburst regions, their chemically primitive gas, and their violent feedback processes, we are not just conducting astronomy, we are directly connecting with the earliest chapters of creation. These galaxies show us that the cosmos we inhabit today, with its grand spirals and massive ellipticals, was once far simpler, more chaotic, and more raw. They remind us that the beauty of the present universe is built upon these small, unruly foundations. The green peas are not just quirky green smudges on a telescope image. They are living fossils of the cosmos, a preserved echo of the time when the first galaxies began transforming darkness into light. They grant us the privilege of seeing, here and now, what would otherwise require us to look back across nearly the entire age of the universe. To study them is to look through a window that time itself has somehow left ajar, giving us a glimpse of a universe billions of years younger, wilder, and filled with the fires of its very first stars. When astronomers talk about green pea galaxies, one of the first points they emphasize is just how rare they truly are. Out of the billions upon billions of galaxies scattered throughout the cosmos, only a few hundred green peas have ever been identified. That's an astonishingly small number, especially when you consider the vast catalogues of galaxies that surveys like the Sloan Digital Sky Survey have mapped. In those immense datasets, where spirals, ellipticals, and irregulars number in the millions, the green peas are statistical outliers, tiny green dots barely visible in the sea of cosmic diversity. Their scarcity immediately sets them apart and raises a pressing question. Why are these galaxies so incredibly uncommon in today's universe? The answer lies in the fact that green peas represent a stage of galactic evolution that is not supposed to exist in the modern cosmos. The universe has aged, galaxies have grown larger, star formation has slowed, and heavy elements have steadily enriched the cosmic environment. Yet the green peas defy this progression. They are chemically primitive, compact, and bursting with newborn stars at a rate that seems more appropriate for galaxies in the early universe than for galaxies existing today. Their very existence is almost a contradiction, a reminder that while most galaxies follow predictable evolutionary paths, a few manage to slip through the cracks and preserve traits from the distant past. This rarity makes them not just interesting, but scientifically invaluable, because each one is a rare jewel carrying critical information about conditions that are nearly impossible to study otherwise. Part of their rarity is also observational. Green pea galaxies are small, faint, and easy to overlook unless you know what to look for. Their striking green glow in Sloan images comes from highly ionized oxygen, but in raw observations, they appear as tiny smudges or dots. Without the collective eyes of thousands of volunteers combing through astronomical data, they may have remained hidden indefinitely. Even now, with astronomers actively searching, only a few hundred examples have been confirmed, and the exact number continues to grow slowly as new surveys dig deeper into the sky. But even if more are found, they will still remain a cosmic minority, vanishingly rare compared to other galaxy types. What's more intriguing is their distribution. Green Pea galaxies don't appear clustered together in large groups like some galaxies do. Instead, they're scattered randomly across the cosmos, isolated pockets of strangeness in an otherwise ordinary universe. This randomness adds to their mystery. Why do these galaxies appear here and there, but not everywhere? Some astronomers suggest that special environmental conditions must exist to allow such a galaxy to form and survive. Perhaps they require unusually pristine gas inflows, or maybe they occupy regions where galactic mergers reignite starbursts in ways that mimic the conditions of the early universe. Whatever the reason, the fact that they are scattered and uncommon reinforces the idea that they are rare cosmic accidents, rather than typical outcomes of galactic evolution. Their rarity also amplifies their scientific importance. When something is common, it becomes easier to generalize about it. But when something is rare, each individual case is precious. Every Green Pea galaxy studied provides unique insights into star formation, radiation leakage, and galactic chemistry. Each one is like a rare fossil find that paleontologists guard carefully because it could change the way we understand the larger story of evolution. Astronomers treat green peas the same way, with reverence and careful analysis, because they know that every spectrum and every image could help unlock mysteries about how galaxies were born and how the universe itself evolved. It's almost poetic that galaxies so tiny and seemingly insignificant in the grand scale of the cosmos turn out to be among the rarest and most important. Their scarcity makes them feel like hidden treasures of the universe, scattered like cosmic emeralds waiting to be found. They are proof that the cosmos still holds surprises, that not everything has been neatly categorized, and that the strangest objects are often the ones that teach us the most. Green Pea galaxies may be few in number, but their impact on astronomy is immense, disproportional to their size and rarity. The discovery of Green Pea galaxies stands as one of the clearest and most inspiring examples of how ordinary people, not just professional astronomers, can fundamentally change our understanding of the universe. Before their discovery, no one had noticed these small, round, green galaxies in survey data. They were hidden among millions of other objects in the Sloan Digital Sky Survey, tiny points of light that, without careful inspection, might easily have been dismissed as noise or insignificant. Yet it was not a state-of-the-art telescope that first brought them to light. It was a global network of volunteers, everyday citizens with curiosity and an internet connection, participating in the Galaxy Zoo project. This project allowed people from all walks of life to classify galaxies, and it was through their collective attention that the green peas were uncovered. Galaxy Zoo operates on a deceptively simple principle. Large datasets of galaxy images are impossible for professional astronomers to classify manually, so volunteers are enlisted to examine each image and categorize the galaxy's shape and appearance. In 2007, as thousands of participants combed through these images, some noticed an unusual pattern: small, bright, and strikingly green, round galaxies that didn't match the standard categories of spirals, ellipticals, or irregulars. They shared their observations on online forums, debated the findings, and repeatedly flagged these anomalies. This grassroots investigation caught the attention of professional astronomers, who realized that these weren't just oddities or errors, they were an entirely new class of galaxy. What began as a hobbyist exercise in pattern recognition quickly became one of the most remarkable discoveries of modern extragalactic astronomy. The role of citizen scientists in this discovery highlights a profound shift in how astronomy can be done in the 21st century. The sheer volume of data produced by modern sky surveys is staggering. Millions of galaxies, billions of stars, and countless other cosmic phenomena are imaged every year. No research team, no matter how large or well-funded, could hope to manually inspect every image. Citizen science projects like Galaxy Zoo democratize this process, turning anyone with curiosity and dedication into a potential discoverer. In the case of the green peas, it was the volunteers' ability to spot patterns and anomalies that machines might have overlooked, combined with the collective scrutiny of thousands of eyes, that made the discovery possible. Another remarkable aspect of this collaboration is the speed and efficiency it enabled. While professional astronomers could have eventually identified green peas through automated algorithms, it likely would have taken far longer, and the discovery might not have attracted the same immediate attention. Humans are exceptionally good at noticing unusual shapes and colors, especially when trained through repeated exposure, and this strength was leveraged to identify something truly unique. By combining human intuition with computational tools, Galaxy Zoo created a system where the rarest and most surprising cosmic objects could be flagged quickly, efficiently, and accurately. In this way, the discovery of Green Pea Galaxies illustrates a new model for how large-scale science can be conducted, a hybrid of professional expertise and the global community's curiosity. The story of Green Pea Galaxies is also inspiring on a personal level. Volunteers who contributed to their discovery were not required to have any formal training in astronomy. Many were simply interested members of the public, motivated by curiosity and the joy of exploration. Their collective efforts demonstrate that science is not confined to laboratories or observatories. It can be a participatory, collaborative endeavor that rewards observation, diligence, and a willingness to question what you see. When citizen scientists noticed these tiny green dots and persisted in investigating them, they proved that even in a field as complex as extragalactic astronomy, ordinary people can make extraordinary contributions. Moreover, the impact of citizen scientists goes beyond the mere act of discovery. Their contributions spark new research directions, open doors to questions that might never have arisen, and help validate findings in ways that are often overlooked. Without the volunteers flagging the green peas, astronomers might have continued to focus on more conventional, larger galaxies, missing out on the rare windows into the early universe that these galaxies provide. The discovery changed not only what we know about galaxies today, but also how we approach the study of galaxy formation, starburst activity, and cosmic reionization. It reshaped the priorities of research in the field. Citizen science also plays a critical role in education and public engagement. The Green Pea story shows that science is not an abstract, untouchable pursuit, but a living, collaborative process in which anyone can participate. Volunteers learn to recognize subtle patterns, understand the basics of astronomy, and engage with complex scientific questions, all while contributing to cutting-edge research. For many participants, being part of the discovery is transformative, fostering a deeper appreciation for the universe and a sense of ownership over the scientific process. It demonstrates that knowledge is not solely the domain of professionals. Rather, it is a shared endeavor in which curiosity, dedication, and observation can lead to real, tangible discoveries. The discovery of Green Pea Galaxies also set a precedent for the potential of future projects. With upcoming telescopes and surveys producing even larger datasets than Sloan, the role of citizen scientists will become increasingly important. Projects like the Vera C. Rubin Observatory and its Legacy Survey of Space and Time, LSST, will generate petabytes of data, creating opportunities for new generations of volunteers to identify rare and unusual cosmic phenomena. Green Pea Galaxies are a proof of concept. They show that even in an era dominated by technology, human eyes, intuition, and collective effort can make discoveries that fundamentally reshape our understanding of the universe. Green Pea Galaxies are not just intriguing for their size, color, or starburst activity. They may hold the key to one of the most transformative periods in cosmic history, the epoch of reionization. To understand this, we need to go back to a time roughly 380,000 years after the Big Bang, when the universe had cooled enough for protons and electrons to combine and form neutral hydrogen atoms. This period, known as the recombination epoch, left the universe filled with a pervasive fog of neutral hydrogen that absorbed ultraviolet light, making the cosmos effectively opaque. This era of darkness persisted for hundreds of millions of years, and astronomers aptly call it the cosmic dark ages. The universe had stars and galaxies forming, but their light was trapped, unable to travel far before being absorbed by the neutral hydrogen. The transition out of this darkness, the epoch of reionization, occurred when something began flooding the universe with energetic radiation capable of ionizing hydrogen, stripping electrons from protons and making the universe transparent to ultraviolet light. For decades, scientists have debated the sources responsible for this ionizing radiation. The leading theory posits that young, compact, star-forming galaxies were the primary contributors. This is where Green Pea Galaxies come into play. They may serve as modern analogues of those early galaxies, providing a tangible laboratory to study the processes that reionize the universe. Green Pea Galaxies are ideal candidates for this role because of their exceptional star-forming activity and their ability to leak ionizing radiation into intergalactic space. Most galaxies today retain a significant portion of the ultraviolet light produced by massive stars within their dense gas clouds, which prevents it from escaping. Green peas, however, appear to be unusually porous. Observations suggest that the intense radiation from their young, hot stars creates channels in their interstellar gas through which ultraviolet photons can escape. These escaping photons are capable of ionizing hydrogen in the surrounding intergalactic medium, much as the first galaxies did billions of years ago. Studying how efficiently green peas allow radiation to escape gives astronomers a concrete way to test models of reionization, which would otherwise rely on indirect observations of galaxies at extreme distances. The mechanisms behind this radiation leakage are complex and fascinating. The intense starburst activity in Green Pea Galaxies produces winds and supernova explosions that carve cavities in the gas, reducing the overall opacity. These cavities act like cosmic funnels, allowing high-energy photons to break free and travel into intergalactic space. In essence, the galaxies are both creating and clearing the paths for ionizing light simultaneously. By measuring the escape fraction of ultraviolet photons, how many manage to leave the galaxy compared to the total produced, astronomers can estimate how many early galaxies of a similar type would have been needed to reionize the entire universe. The numbers suggest that even a modest population of galaxies with green pea-like characteristics could have played a dominant role in lifting the cosmic fog. Furthermore, the low metallicity of Green Pea Galaxies strengthens the connection to the early universe. In the infancy of cosmic history, stars formed from almost pristine hydrogen and helium, lacking the heavy elements created by previous generations of stars. The massive stars in these chemically primitive galaxies are hotter and more efficient at producing ionizing radiation than stars in metal-rich environments. Green Pea Galaxies mirror these conditions today, making them near-perfect analogues of the galaxies that first illuminated the cosmos. By studying them, astronomers can refine models of how much ultraviolet light early galaxies emitted, how far it traveled, and how quickly the dark ages ended. Another compelling aspect is their compactness. Because green peas are small and intensely concentrated, the star-forming regions are highly energetic relative to their size. This means that the effects of ionizing radiation are more pronounced, creating localized regions of reionization that can be mapped and analyzed. By observing multiple green pea galaxies, astronomers can simulate how clusters of such galaxies would have contributed to the large-scale reionization of the universe. It's a remarkable connection. Tiny, nearby galaxies acting as stand-ins for ancient cosmic engines that reshape the universe on scales of millions of light-years. The study of green pea galaxies also provides insight into why reionization did not happen uniformly. Some regions of the early universe remained neutral longer than others, and variations in galaxy density, star formation rates, and radiation leakage likely caused these disparities. Green peas demonstrate that even today, galaxies can have vastly different capacities to emit ionizing photons depending on their internal structure, starburst intensity, and gas distribution. By examining these variations in nearby examples, astronomers gain a better understanding of how patchy or gradual the reionization process might have been, and how certain regions of the universe became transparent before others. Ultimately, green pea galaxies are a bridge between the ancient and the modern cosmos. They allow scientists to directly study the physical processes that ended the universe's dark ages, providing empirical evidence for theories that would otherwise be tested only on the basis of extremely distant, faint, and challenging observations. They show us that even in today's universe, small, compact galaxies can play outsized roles in shaping their environments, mirroring the transformative effects early galaxies had on the intergalactic medium. Without objects like green peas, much of what we know about cosmic reionization would remain speculative, relying solely on models and the light of galaxies billions of light-years away. In essence, these tiny green galaxies are not just curiosities, they are relics, laboratories, and guides to one of the most pivotal events in cosmic history. Their study connects us to the first billion years of the universe, revealing how the earliest stars and galaxies brought light to a once dark cosmos, enabling the rich, luminous universe we observe today. In every beam of escaping ultraviolet radiation, green peas echo the processes that transform the universe from opaque and dark to transparent and vibrant, reminding us of the profound connections between the distant past and the cosmic present. One of the most remarkable features of green pea galaxies is their chemical composition, or rather the lack of heavy elements, which astronomers refer to as metals. In the universe, elements heavier than hydrogen and helium, like carbon, oxygen, nitrogen, and iron, are forged in the cores of stars and distributed into space through supernova explosions and stellar winds. Over billions of years, galaxies like the Milky Way have undergone countless cycles of star formation, producing and recycling these heavy elements to enrich their gas, dust, and subsequent generations of stars. Green pea galaxies, in contrast, are chemically primitive. Their metallicity is extremely low, often only a fraction of that found in the Milky Way, which indicates that they have experienced far fewer cycles of star formation and chemical enrichment. This makes them living examples of galaxies that have retained the characteristics of the early universe. The low metallicity of green peas has profound implications for their physics and appearance. Metals in a galaxy's gas can cool the material, allowing it to condense and form stars more easily. With fewer metals, the gas in green pea galaxies remains hotter and more diffuse. Yet paradoxically, these galaxies are able to sustain extremely intense star formation. This unusual combination, primitive chemistry paired with extreme stellar production, challenges traditional models of star formation and galactic evolution. It forces astronomers to reconsider the relationship between chemical enrichment and the ability of a galaxy to produce stars efficiently, revealing that under the right conditions, low-metallicity systems can act as incredibly vigorous stellar nurseries. Another consequence of their low metal content is the effect on their light. Massive stars in metal-poor galaxies are hotter and bluer than their metal-rich counterparts because metals absorb and redistribute some of the star's energy. In green peas, this contributes to their intense ultraviolet output, which in turn is responsible for their ability to ionize surrounding hydrogen and potentially replicate the conditions that raionize the early universe. Their spectra, dominated by lines from ionized oxygen, hydrogen, and helium, provide a clear chemical fingerprint that tells astronomers they are observing something very different from the typical evolved galaxies in the local universe. Every measurement of metallicity, every spectral line, is a clue pointing back to their primitive origins and offering insight into the processes that dominated in the first billion years of cosmic history. Low metallicity also affects the life cycle of stars within Green Pea Galaxies. Stars formed in such environments are more likely to be massive, short-lived, and capable of producing extreme feedback into their surroundings. Supernovae from these stars enrich the surrounding gas and drive powerful winds, shaping the galaxy's evolution while simultaneously making it possible for ionizing radiation to escape. In this way, the chemical primitiveness of green peas is intimately linked to their dynamic behavior. The lack of metals is not just a passive feature. It actively contributes to the extraordinary energy output, rapid star formation, and structural peculiarities that make these galaxies so compelling to study. Furthermore, their low metallicity provides a natural laboratory for understanding the early stages of galaxy formation. By examining how stars form and evolve in such metal-poor environments, astronomers can model the behavior of the very first stars in the universe, known as population 3 stars. These ancient stars were composed almost entirely of hydrogen and helium, and they played a critical role in shaping the first galaxies, initiating chemical enrichment, and influencing the surrounding intergalactic medium. Green Pea Galaxies, with their similar conditions, allow scientists to test these theories in real time, offering observable examples of how stars and galaxies behave in nearly pristine environments. The chemical simplicity of green peas also contributes to their rarity and uniqueness. Most galaxies in the modern universe have experienced enough generations of star formation that low metallicity conditions are exceedingly uncommon. The fact that these galaxies exist today, chemically young in a universe more than 13 billion years old, raises important questions about their formation, survival, and evolutionary history. Did they form in isolation, avoiding mergers that would have enriched them? Were they rejuvenated by inflows of pristine gas that diluted their metallicity? Or are they relics of an earlier cosmic epoch, preserved in unusual environments that shielded them from typical evolutionary processes? The answers are still being debated, but the metal-poor nature of green peas ensures that each discovery challenges astronomers to refine their understanding of how galaxies evolve over billions of years. Moreover, their chemical primitiveness makes green pea galaxies invaluable for calibrating models of star formation and feedback in low metallicity environments. They provide a benchmark for testing how stars inject energy into the surrounding gas, how ionizing radiation escapes, and how metals are produced and distributed in young galaxies. Without examples like green peas, these models would have to rely solely on simulations or the study of distant, faint galaxies, which are much harder to observe in detail. In this sense, green peas are a bridge between theoretical predictions and real, observable cosmic laboratories. The formation of green pea galaxies is a puzzle that continues to intrigue astronomers because it seems to defy the natural progression of cosmic evolution. Most galaxies in the modern universe have already undergone billions of years of star formation, mergers, and chemical enrichment, gradually evolving into the spirals, ellipticals, and irregulars that populate the sky today. By contrast, green pea galaxies appear almost as if they've been plucked from the early universe and set down in the present, retaining traits that are expected only in galaxies formed billions of years ago. Their small size, high star formation rates, low metallicity, and ability to leak ionizing radiation make them resemble primordial galaxies, yet they exist in a universe where such conditions are exceedingly rare. This raises an essential and still unresolved question. How did they form, and why have they persisted in this seemingly arrested state while most galaxies matured and evolved long ago? One leading theory suggests that green pea galaxies may form in isolated or special environments that allow them to remain relatively untouched by the cosmic processes that shape typical galaxies. Most galaxies undergo mergers, accrete gas from neighboring systems, and recycle their materials through repeated generations of stars, processes that enrich their chemical composition and change their structure over time. If a galaxy exists in a more secluded region of space, free from significant interactions with neighbors, it may retain its primordial characteristics for much longer. In this scenario, green peas could represent a rare survival of galactic archetypes that have largely disappeared elsewhere, offering a direct glimpse into conditions that were once common in the early universe. Another possibility is that green pea galaxies are products of recent events that have triggered unusual star formation. In this view, they may not be truly ancient, chemically primitive relics, but rather galaxies that have undergone a sudden inflow of pristine, metal-poor gas from the intergalactic medium. This infusion of new material can reset the galaxy, diluting its metal content and fueling an intense burst of star formation that mimics the characteristics of primordial galaxies. The result is a system that appears young, both chemically and in terms of star formation, despite existing in a universe that has aged over 13 billion years. Observations of gas dynamics and kinematics in green pea galaxies suggest that this may indeed be a factor, as some show evidence of inflows and outflows consistent with rapid gas accretion. The compactness and intense star formation of green peas may also hint at their origin. Many of these galaxies are thought to be in a transient evolutionary stage, a short-lived burst of activity that will eventually settle into a more quiescent state. Their size and high-density star-forming regions make them unstable, susceptible to internal feedback from supernovae and stellar winds that could disrupt gas distribution and alter the course of their evolution. In this sense, the green peas we observe today may be caught in the act of a rare and brief stage of galactic development, a fleeting snapshot that provides invaluable insight precisely because it is so unusual. The rarity of this phase may explain why only a few hundred have been identified. Many galaxies likely pass through similar stages too quickly or under less observable conditions to be noticed. Yet another layer of mystery lies in their ability to leak ionizing radiation. For a galaxy to allow ultraviolet photons to escape, it must have a particular combination of star formation, gas distribution, and structural porosity. Not every galaxy can achieve these conditions, especially in the modern universe, where gas is often more enriched and settled. The fact that green peas do exhibit this property suggests that either they formed under extremely specific conditions, or that they underwent unique evolutionary processes that sculpted them into efficient emitters of ionizing light. Understanding why these conditions exist in the modern cosmos remains an open question, and each new observation adds a piece to the puzzle, highlighting both the complexity and the rarity of these objects. Moreover, the mystery of their formation is intertwined with the broader questions of galaxy evolution. Are Green Pea Galaxies examples of primordial systems that simply survived untouched? Are they rejuvenated by fresh gas inflows? Or are they unique evolutionary experiments, rare combinations of environmental factors, star formation processes, and chemical conditions that produce a galaxy unlike almost anything else in the nearby universe? Current data suggests that the answer may be a combination of these factors. Some green peas may indeed be ancient relics, while others may be products of recent cosmic events that have temporarily reset their evolution. Distinguishing between these possibilities requires detailed studies of their stellar populations, gas content, and dynamics. Work that is ongoing and pushing the limits of modern observational astronomy. Adding to the intrigue is the contrast between green peas and other rare galaxies. Unlike massive ellipticals or spirals, which dominate the local universe, or exotic objects like ultra-diffuse galaxies or ringed systems like Hoag's object, green peas are small, vibrant, and highly energetic. Their energy output relative to their size is extraordinary, suggesting that whatever process formed them or kept them in this state is highly efficient. Each new discovery challenges existing models and forces astronomers to re-evaluate assumptions about what kinds of galaxies can exist in the contemporary universe. In this way, the mystery of their formation is not just about tracing their origin, but about testing our understanding of galaxy evolution itself. In essence, the very existence of green pea galaxies in today's universe serves as a cosmic paradox. They are chemically primitive, extraordinarily compact, and intensely star-forming, traits that should have been left behind billions of years ago. Their survival or recent rejuvenation challenges the standard narrative of galaxy evolution and opens new avenues of inquiry into how galaxies form, evolve, and interact with their environment. Each observation raises new questions. Why do they exist in isolation? How do they sustain their extreme starburst activity? Why is their metal content so low despite existing in a chemically mature universe? These questions remain largely unanswered, making green pea galaxies one of the most enigmatic and scientifically valuable classes of galaxies known. Green pea galaxies offer a unique and tantalizing window into the process of galaxy evolution, providing astronomers with a glimpse of systems caught in an unusual and fleeting stage of development. Unlike mature galaxies such as the Milky Way, which have settled into stable forms with predictable star formation rates and well-mixed chemical compositions, green peas appear to be in a state of rapid transformation. They are small, intensely star-forming, and chemically primitive, resembling galaxies from the early universe, yet they exist in a modern cosmic epoch. This combination of characteristics suggests that we are observing them during a transitional phase, a momentary evolutionary window that allows scientists to study extreme starburst activity, ionizing radiation escape, and structural development all at once. By understanding these transitional systems, astronomers can fill in critical gaps in the narrative of how galaxies grow, evolve, and eventually settle into more quiescent forms. The notion of green peas as transitional galaxies stems in part from their intense but short-lived star formation activity. Starburst phases, by nature, are temporary. The gravitational collapse of dense gas clouds triggers rapid star formation, producing clusters of massive hot stars that shine brightly in ultraviolet and visible light. These bursts do not last forever. Stellar winds, supernova explosions, and radiation feedback soon disperse gas, quenching star formation and altering the galaxy's dynamics. In Green Pea Galaxies, we are likely seeing the peak of such bursts. A snapshot in which the system is dramatically transforming itself from a relatively compact, low-metallicity galaxy into something potentially more diffuse and chemically enriched. Observing these galaxies during this stage is a rare opportunity, because such bursts occur quickly on cosmic timescales and are easily missed, if not actively searched for. Their transitional nature also extends to their structure and dynamics. Green Pea galaxies are remarkably compact, yet their stellar populations and ionized gas indicate that energetic feedback from young stars is already reshaping the interstellar medium. Supernova explosions and stellar winds create outflows of gas, forming cavities and tunnels that allow ionizing radiation to escape. These processes not only regulate star formation within the galaxy, but also affect the surrounding intergalactic medium, influencing the galaxy's environment in ways that are rarely observed in larger, more settled systems. By studying green peas, astronomers can directly observe how star formation drives feedback, how gas is redistributed, and how structural changes unfold in real time, offering a laboratory for phenomena that are normally inferred only from distant or post-starburst galaxies. Another aspect of their transitional status lies in their chemical evolution. Green Pea galaxies are metal-poor compared to most galaxies in the nearby universe, yet the intense starburst activity means that metals are being produced at a rapid rate. In essence, these galaxies are in the midst of chemical transformation. Hydrogen and helium are being fused into heavier elements, and stellar feedback is beginning to enrich the surrounding gas. Studying these galaxies allows astronomers to see chemical enrichment as it happens, rather than inferring it from older, evolved systems. This real-time view provides critical insight into how galaxies gradually increase their metallicity over billions of years, and how star formation rates, feedback, and gas inflow work together to shape chemical evolution. The rarity of Green Pea galaxies also underscores their transitional nature. Their properties are unusual enough that they do not conform to typical classifications, sitting at an extreme end of the galaxy population spectrum. Most galaxies have long since settled into slower star formation and higher metallicity states, making green peas exceptional laboratories for studying what happens when galaxies deviate from the norm. They may represent a type of galaxy that is almost always short-lived or difficult to observe, a fleeting moment in the cosmic timeline that offers insights impossible to gain from more common, long-lived systems. Every observation adds to the understanding of how rare, intense starburst episodes contribute to galaxy growth and evolution. Furthermore, Green Pea galaxies illuminate the broader continuum of galaxy evolution. By comparing them to both ancient, distant galaxies and local, mature systems, astronomers can trace the progression from initial formation through rapid starburst phases to quiescent maturity. Green peas may illustrate a middle chapter in this progression. Galaxies that have not yet settled into stability, but are no longer primordial in the strictest sense. They show that galaxy evolution is not a uniform, linear process, but can include intermittent bursts, chemical resets, and feedback-driven structural transformations. In other words, these galaxies are evidence that evolution is dynamic and can produce extreme and unexpected states even in the relatively modern universe. Studying green peas also provides valuable insight into the factors that drive galactic diversity. Why do some galaxies become massive spirals, while others remain compact, starbursting systems? Why do certain galaxies retain primordial characteristics, while the majority evolve rapidly? By analyzing the properties of green peas, such as their star formation rates, gas density, metallicity, and radiation leakage, astronomers can refine models of galaxy formation and evolution, testing hypotheses about the roles of environment, gas inflow, and feedback mechanisms. Each green pea observed serves as a live case study of these processes in action, offering concrete data that illuminate the diversity of pathways through which galaxies evolve. In addition, the transitional status of Green Pea Galaxies has implications for understanding extreme cosmic events, such as cosmic reionization and the creation of massive star clusters. By witnessing galaxies that are actively generating intense radiation, shaping their gas content, and producing clusters of massive stars, astronomers can extrapolate these processes to the early universe. In essence, green peas allow scientists to simulate and study phenomena that would have occurred during the first billion years of cosmic history, providing a bridge between local, observable galaxies and the faint, distant systems seen in high redshift surveys. Astronomers' fascination with green pea galaxies stems from the extraordinary combination of their rarity, their extreme properties, and the unique scientific window they provide into processes that shaped the early universe. In traditional studies of galaxy formation, astronomers are often constrained to observing galaxies at vast distances, billions of light-years away. While these distant galaxies carry the signatures of the early cosmos, their faintness and the limits of even the most powerful telescopes make detailed study challenging. Light from these galaxies has traveled for billions of years, often redshifted into infrared wavelengths, leaving only coarse spectral and photometric information for analysis. Green pea galaxies, in contrast, are relatively nearby. Despite their small size, they can be observed in remarkable detail using modern telescopes, allowing scientists to obtain precise measurements of their chemical composition, star formation rates, radiation output, and internal dynamics. This proximity provides a rare laboratory to study early universe processes in the present-day cosmos. One of the most compelling reasons for astronomers' obsession is the green peas' ability to emulate conditions that existed during the epoch of cosmic reionization. As previously discussed, these galaxies produce intense ultraviolet radiation capable of escaping into intergalactic space, ionizing hydrogen gas. In the distant early universe, similar galaxies were likely responsible for transforming the cosmos from opaque to transparent. Yet those galaxies are so far away that direct observation of their properties is extraordinarily difficult. Green peas, being nearby analogues, allow astronomers to study the same physical processes: massive star formation, ultraviolet photon leakage, and feedback-driven gas dynamics in exquisite detail. They are effectively living models of ancient galaxies, providing the chance to experimentally test theories that would otherwise remain largely hypothetical. Their extreme star formation rates also capture attention. In many ways, green pea galaxies are cosmic overachievers. They are tiny in size, sometimes only 1/10 the mass of the Milky Way, yet they generate star formation at rates up to 10 times higher than typical galaxies of similar size. This extraordinary efficiency allows astronomers to study the mechanisms that drive rapid starbursts. For instance, how do dense gas clouds collapse under gravity? How do feedback processes regulate star formation? And how does gas inflow sustain such bursts over relatively short timescales? Observing these mechanisms in green peas provides insights into the physics of star formation under extreme conditions, which are otherwise difficult to replicate in either local, massive galaxies or in distant high redshift systems. Chemical composition adds another layer of scientific value. Green peas are metal poor, meaning they closely resemble the chemical conditions of the earliest galaxies. This enables astronomers to study stellar populations and evolution in environments that are rare today but dominated the early universe. They can observe how massive stars behave when metals are scarce, how supernovae disperse elements, and how early galaxies might have evolved chemically. These observations refine theoretical models of population 3 stars, galactic chemical enrichment, and early starburst activity, phenomena that shaped the evolution of the universe as a whole. Green peas also offer insight into the escape of ionizing radiation, a process critical for cosmic reionization. By measuring the fraction of ultraviolet light that escapes these galaxies, astronomers can directly test models of how early galaxies cleared the cosmic fog, influencing the transparency of the universe. Such studies are virtually impossible in distant galaxies, where absorption by intervening gas clouds and faintness obscure the relevant signals. In green peas, the radiation is strong enough and the galaxies are close enough to allow precise spectroscopy, mapping of ionized regions, and detailed examination of how radiation interacts with gas. This makes them invaluable tools for connecting local observations with cosmic-scale processes. The structural and dynamical characteristics of green peas are equally fascinating. These galaxies are compact, turbulent, and bursting with energy, yet they often show little sign of large-scale rotation or the ordered structures seen in spirals. By studying how gas and stars move within them, astronomers gain insight into the formation of irregular, early-type galaxies and the role of turbulence in star formation. Their peculiar morphologies, rounded, pea-like shapes with bright emission regions, offer a contrast to the majority of local galaxies and challenge conventional assumptions about galaxy morphology. Understanding how these systems maintain structural integrity while undergoing intense star formation provides clues to the balance of gravitational, thermal, and radiative forces in small, energetic galaxies. Another factor driving astronomers' obsession is the rarity and uniqueness of green peas. Their scarcity makes each one precious for study. Unlike common galaxy types, where patterns can be statistically analyzed across large populations, green peas are exceptional cases, and every observation can yield new, unexpected insights. The combination of proximity, extreme star formation, low metallicity, and unusual morphology means that they provide a multifaceted perspective on galaxy evolution, essentially packing billions of years of cosmic history into compact, observable systems. Beyond the scientific specifics, Green Pea Galaxies capture the imagination because they challenge preconceived notions about the modern universe. They show that even today, when the cosmos has largely settled into familiar patterns of spiral and elliptical galaxies, tiny anomalies exist that retain the physics, chemistry, and behavior of the distant past. This makes them not only scientifically valuable, but also philosophically intriguing, reminding astronomers that the universe is dynamic and full of surprises, and that even in nearby space, relics of cosmic youth can persist in unexpected forms. Studying green pea galaxies presents a formidable challenge for astronomers, despite their relative proximity compared to the distant galaxies they emulate. Their small size and compact nature, which make them so scientifically valuable, also make them inherently difficult to observe in detail. Most green peas are tiny, often only a few thousand light-years across, a fraction of the Milky Way's diameter. And their faintness means that even though they shine brightly in certain wavelengths, their overall light output is modest. This requires the use of highly sensitive instruments capable of detecting faint signals with high precision, particularly when trying to analyze their spectra, map star formation regions, or measure gas dynamics. Even with modern telescopes, these galaxies challenge observers to push the limits of resolution and sensitivity, demanding long exposure times and careful data reduction to separate subtle features from noise. The faintness of green pea galaxies is compounded by the fact that much of their defining emission comes in specific spectral lines, such as the bright green light from highly ionized oxygen. Observing these features requires instruments capable of high spectral resolution and the ability to isolate specific wavelengths amidst background noise from the night sky and other cosmic sources. Ground-based telescopes, while powerful, must contend with atmospheric distortion, which can blur the already compact galaxies and make it difficult to distinguish fine details. Space-based telescopes, such as Hubble, can provide the necessary clarity, but their time is highly competitive, and only a limited number of green peas can be studied in sufficient depth. Consequently, detailed surveys of these galaxies are painstaking and require careful planning, often involving coordinated observations across multiple telescopes and wavelengths. Another obstacle is the sheer rarity of Green Pea galaxies in the modern universe. With only a few hundred identified so far, astronomers cannot rely on large samples to average out observational uncertainties. Each galaxy must be studied individually, which magnifies the importance of every measurement and increases the pressure on researchers to obtain accurate, high-quality data. Unlike more common galaxy types, where statistical analyses can reveal general trends, green peas demand case-by-case scrutiny, which consumes significant observational resources. This scarcity also means that researchers must continuously scan large sky surveys to identify new candidates, often relying on projects like the Sloan Digital Sky Survey, SDSS, or citizen science initiatives like Galaxy Zoo to pinpoint these elusive objects. Even when a green pea is successfully identified, probing its internal structure is exceptionally challenging. These galaxies are highly compact, with star-forming regions that are densely packed into small volumes. Resolving these individual regions requires the highest resolution imaging available, often approaching the diffraction limits of telescopes. Adaptive optics on ground-based telescopes can help, but even then, the smallest features remain difficult to separate. Mapping the motions of stars and gas within these galaxies, which is crucial for understanding their dynamics and feedback processes, demands high-resolution spectroscopy with long integration times. Detecting outflows of ionized gas or tracing the escape of ultraviolet radiation requires specialized instrumentation sensitive to faint signals in specific wavelengths, adding another layer of complexity to their study. Multi-wavelength observations are also essential, but technically demanding. Green Pea galaxies emit light across the spectrum, from ultraviolet to optical, and even into the infrared. Each wavelength provides distinct insights. Ultraviolet traces young, massive stars. Optical emission lines reveal gas composition and star formation rates. Infrared observations can uncover hidden dust and cooler stellar populations. Coordinating observations across these different regimes is logistically complex, requiring careful calibration to ensure that data from multiple instruments and observatories can be accurately combined. The faintness of green peas means that long exposures are needed at each wavelength, further increasing the time and effort required to obtain a comprehensive picture. Furthermore, studying the escape of ionizing radiation, a key property of green peas, is exceptionally difficult. Ultraviolet photons capable of ionizing hydrogen are easily absorbed by interstellar gas, dust, and even the Earth's atmosphere, necessitating space-based observatories for direct detection. Observing these photons requires sensitive ultraviolet spectrographs, which are limited in number and availability. Even with the most powerful instruments, detecting the fraction of escaping radiation with confidence is challenging due to interference from intervening gas and background sources. Researchers must use sophisticated models and careful interpretation to distinguish the galaxy's intrinsic radiation from external effects, adding layers of computational complexity to the observational challenge. The combination of small size, faintness, rarity, and the need for multi-wavelength, high-resolution observations makes Green Pea galaxies some of the most technically demanding targets in modern astrophysics. Each galaxy studied requires a carefully orchestrated campaign, often blending ground-based and space-based observations, spectroscopy, and imaging to build a complete picture. Despite these difficulties, the scientific payoff is immense. Every new measurement provides insight into star formation, chemical evolution, radiation leakage, and galaxy dynamics under extreme conditions, effectively turning green peas into natural laboratories for understanding early universe processes in the nearby cosmos. In addition to observational challenges, theoretical modeling of green pea galaxies is also complex. Their unusual combination of properties, high star formation rates, low metallicity, compact structure, and ionizing photon escape, requires sophisticated simulations to reproduce their behavior accurately. These models must account for gas dynamics, radiative feedback, star formation efficiency, and chemical evolution, often in three-dimensional simulations with extremely high resolution. Validating these models requires detailed observational data, which, as described, is challenging to acquire, creating a feedback loop where observational limitations directly impact theoretical understanding. Despite these hurdles, advances in telescope technology, spectroscopy, and computational modeling are gradually peeling back the layers of mystery surrounding green pea galaxies. Observatories like Hubble, the Very Large Telescope, VLT, and upcoming facilities like the James Webb Space Telescope, JWST, provide unprecedented clarity and sensitivity, enabling astronomers to explore their internal structures, chemical composition, and radiation leakage in ways previously impossible. Each new study pushes the boundaries of what can be observed and measured, transforming these tiny, faint objects into keystones for understanding some of the most profound questions in cosmology. Green pea galaxies occupy a unique niche in the landscape of rare and unusual galaxies, and comparing them to other cosmic oddities helps highlight just how distinct they are. Take Hoag's object, for instance, a striking ring galaxy with a nearly perfect circular ring of young blue stars surrounding a yellowish core. While visually spectacular and certainly uncommon, Hoag's object represents an entirely different evolutionary story. It is relatively massive, structurally coherent, and exhibits a type of star formation that is confined to its ring. Green pea galaxies, in contrast, are tiny, compact, and intensely star-forming throughout their entire volume rather than just in a ring. Their peculiar green glow, low metallicity, and extreme radiation leakage set them apart as objects of intense scientific interest rather than simply aesthetic fascination. Where Hoag's object is a masterpiece of galactic architecture, green peas are laboratories for understanding fundamental cosmic processes. Ultra-diffuse galaxies provide another intriguing contrast. These are ghostly, enormous galaxies with the stellar mass of a dwarf galaxy but spread over an area comparable to the Milky Way. They are faint, diffuse, and often dark matter dominated, with very little active star formation. Their extreme size and tenuous structure make them fascinating for studying dark matter and galaxy formation under unusual conditions. Green pea galaxies, by contrast, are the antithesis in terms of density and activity. They are small, extremely compact, and bursting with star formation, with most of their mass concentrated in a bright, active core. Whereas ultra-diffuse galaxies teach astronomers about quiescence and the gravitational scaffolding of galaxies, green peas reveal how a galaxy can sustain extreme energetic output in a chemically primitive state, making them complementary examples of how diverse galactic evolution can be. Other peculiar galaxies, such as polar ring galaxies or irregular dwarfs, also illustrate the diversity of galactic forms, but none combine the properties that make green peas so exceptional. Polar ring galaxies, for example, are defined by their perpendicular rings of stars and gas, often the result of a merger or accretion event. While this morphology is rare, these systems are generally larger and more chemically evolved than green peas, and they do not exhibit the extreme star formation or ultraviolet radiation leakage that defines the latter. Irregular dwarf galaxies may share some similarities with green peas in size or metallicity, but they rarely reach the same star formation rates or display the same compact intensity. Green peas, therefore, stand out even among other outliers as a truly extreme subset of the galactic population. From a scientific perspective, what makes these comparisons valuable is that they contextualize green pea galaxies within the broader spectrum of cosmic oddities. While Hoag's object captivates with symmetry and ultra-diffuse galaxies intrigue with their ghostly mass, green peas provide data that directly informs our understanding of galaxy formation, chemical evolution, starburst activity, and cosmic reionization. They are not just anomalies, they are functional examples of extreme physics in action, bridging the gap between theoretical predictions about early galaxies and observable phenomena in the local universe. By situating them alongside other rare galaxies, astronomers can better appreciate both their uniqueness and the lessons they offer about the diversity of cosmic structures. Interestingly, this comparison also highlights the importance of scale, density, and activity in defining a galaxy's evolutionary path. Hoag's object is massive and stable. Ultra-diffuse galaxies are sprawling and quiescent, and green peas are tiny yet hyperactive. Each represents a different experiment in galaxy evolution: stability versus turbulence, isolation versus density, quiescence versus extreme star formation. In this light, green peas occupy a rare niche that no other known galaxy type replicates, making them an indispensable piece of the cosmic puzzle. Moreover, the contrasts reinforce why green peas are such critical objects for testing theories of the early universe. Whereas distant, high redshift galaxies provide snapshots of the past, and rare morphologies like Hoag's object or ultra-diffuse galaxies demonstrate extreme outcomes of cosmic processes, green peas allow astronomers to study in nearby space the same physical processes that occurred billions of years ago. They combine rarity, proximity, and extreme behavior in a way that is unparalleled, serving as a bridge between theory and observation. Observing them alongside other rare galaxies underscores just how unusual their combination of properties is, cementing their status as unique laboratories for the study of galaxy formation and evolution. Green Pea Galaxies occupy a pivotal position in the cosmic story, acting as a missing puzzle piece in our understanding of how galaxies and the universe itself evolved over billions of years. The universe is a vast, complex web of matter, energy, and structure, and astronomers rely on studying galaxies of various sizes, types, and ages to piece together its history. Most galaxies we observe today are massive, chemically evolved, and relatively stable, giving only limited insight into the earliest stages of galactic life. High redshift galaxies, on the other hand, exist at immense distances and are so faint that studying their internal processes is challenging. Green Pea Galaxies bridge this gap, providing nearby, accessible laboratories where extreme conditions reminiscent of the early universe can be directly observed. Their existence helps astronomers link the properties of modern galaxies with those that dominated the first billion years after the Big Bang, effectively filling in a critical chapter in the evolutionary narrative. These galaxies are crucial for understanding how star formation and chemical evolution proceed under extreme conditions. In the early universe, galaxies formed from nearly pristine hydrogen and helium gas, generating the first stars and enriching their surroundings with heavier elements through supernovae. Green Pea galaxies, with their low metallicity and intense star-forming activity, are modern analogues of these primordial systems. By studying them, scientists can observe processes such as rapid gas collapse, feedback from young massive stars, and ultraviolet radiation leakage in a setting that is close enough to resolve in detail. This allows researchers to validate models of early galaxy evolution, test predictions about starburst mechanisms, and better understand the formation and distribution of chemical elements, insights that would otherwise be accessible only through indirect observation of distant, faint galaxies. Green Pea Galaxies also illuminate the role of rare, high-energy events in cosmic history. Their extreme star formation rates, combined with their compact size, suggest that short-lived but powerful bursts of activity can dramatically alter a galaxy's evolution. These bursts produce copious amounts of ionizing radiation, drive outflows of gas, and shape the internal dynamics in ways that influence both the galaxy itself and its surrounding intergalactic environment. Understanding these events is essential to reconstructing the conditions that prevailed during cosmic reionization, the epoch when ultraviolet light from the first galaxies ionized neutral hydrogen and made the universe transparent to light. Green peas thus serve as tangible examples of phenomena that were pivotal in transforming the cosmos but are otherwise difficult to study due to their distance and faintness in the early universe. Moreover, green pea galaxies act as a key link between theory and observation. Computational models of galaxy formation predict a wide variety of evolutionary pathways, but validating these models requires observational evidence of galaxies in extreme or transitional states. Green peas fulfill this need perfectly. They are compact, high-energy systems that test the limits of our understanding of star formation, feedback, and chemical evolution. Each galaxy observed contributes to a more complete picture of how galaxies grow, interact with their environment, and evolve over cosmic time. They provide a critical checkpoint for theory, confirming or challenging predictions, and refining our comprehension of the forces that govern the cosmos. Their role as a puzzle piece is further underscored by their rarity. Only a few hundred green pea galaxies have been identified in modern surveys, highlighting that they represent a fleeting or unusual evolutionary phase. Such scarcity emphasizes their importance. While common galaxies provide broad statistical information, rare systems like green peas reveal the extremes of galactic behavior and the boundary conditions of galaxy formation. They allow astronomers to explore questions about what is possible in galactic evolution, offering insight into the processes that may have been more widespread in the early universe, but are now largely absent. This makes them indispensable for constructing a holistic understanding of the cosmic timeline, from the primordial formation of the first stars to the complex galactic ecosystems observed today. Green pea galaxies also help clarify the connection between micro and macro-scale processes in the universe. At the scale of individual stars and gas clouds, these galaxies reveal the mechanics of star formation, supernova feedback, and ionizing radiation escape. At the cosmic scale, they inform models of how galaxies collectively influenced the intergalactic medium, contributed to reionization, and enriched the universe with heavier elements. By linking processes across these scales, green peas become an integrative element in the puzzle of cosmic evolution, connecting the physics of individual galaxies to the history of the universe as a whole. In addition, these galaxies highlight the diversity and adaptability of galactic systems. Their extreme compactness, low metallicity, and intense star formation demonstrate that galaxies do not follow a single evolutionary path. Rather, they can exhibit extraordinary variations depending on environmental factors, gas inflows, and internal dynamics. Observing green peas thus expands our understanding of what galaxies are capable of achieving and how they can survive or thrive under conditions that differ drastically from the more typical massive spirals and ellipticals. They are reminders that the universe is not uniform in its evolution, and that rare systems often hold the key to understanding the full range of cosmic phenomena. Green Pea galaxies are, in every sense, cosmic marvels that challenge our understanding and ignite our imagination. Despite their small size, these tiny galaxies hold an outsized significance in the grand tapestry of the universe, acting as living laboratories that allow us to witness processes usually hidden in the distant past. They are reminders that the universe is not just a collection of massive spirals and elliptical giants. It is a place where the unusual, the extreme, and the fleeting can emerge and persist, sometimes in the most unassuming forms. Their pea-like shapes and green glow, once a quirky anomaly noticed by citizen scientists, now symbolize one of the rarest and most instructive types of galaxies in existence, combining extreme star formation, low metallicity, and intense radiation output in a package that seems almost impossibly compact. What makes green peas particularly enchanting is how they encapsulate both the mystery and the accessibility of the cosmos. They are nearby enough for detailed study, yet rare enough to maintain an aura of exclusivity, a treasure trove for astronomers seeking to understand the universe's earliest epochs. Each observation reveals new layers of complexity, from turbulent star-forming regions to chemically primitive gas clouds, and from ultraviolet radiation escaping into intergalactic space to subtle structural features that hint at their evolutionary path. They are small but potent, a paradoxical combination of fragility and power that mirrors the universe itself, where the tiniest objects can have profound implications. These galaxies also serve as a testament to human curiosity and collaboration. Their discovery, driven by ordinary people participating in the Galaxy Zoo project, underscores the notion that groundbreaking scientific insights are not confined to elite laboratories. Sometimes they emerge from the collective curiosity of citizens around the world. The fact that these unassuming, green-hued dots in telescope images could revolutionize our understanding of cosmic evolution emphasizes that the universe still has secrets hiding in plain sight, waiting for those who look closely enough to notice. It reminds us that even in a cosmos filled with grandiose structures, supermassive black holes, sprawling spiral arms, and luminous quasars, the most extraordinary revelations can come from the smallest, most overlooked corners. Green Pea galaxies also inspire awe because they embody the persistence of primordial conditions in the modern universe. While most galaxies have long since evolved into chemically enriched, stable systems, green peas retain characteristics of the first galaxies: rapid star formation, low metal content, and the ability to emit ionizing radiation into space. In observing them, astronomers are peering into a cosmic time capsule, glimpsing a universe as it might have appeared billions of years ago, all without leaving the relative proximity of the local cosmos. Their very existence challenges assumptions about galactic evolution and demonstrates that the universe is capable of maintaining anomalies, exceptions, and rare phenomena that defy conventional expectations. Moreover, their striking green emission is more than just visually captivating. It is a signature of highly ionized oxygen, evidence of intense ultraviolet radiation and powerful star-forming activity. This glow is a vivid marker of processes that are critical to cosmic history, including the potential mechanisms that reionized the universe after the cosmic dark ages. In every spectrum and image, green peas convey a story of energy, transformation, and the intricate interplay of physics and chemistry that governs the birth and evolution of galaxies. They are simultaneously simple in appearance and profoundly complex in behavior. a duality that captures the imagination of scientists and enthusiasts alike. In the broader cosmic context, Green Pea Galaxies exemplify the unexpected diversity of the universe. While astronomers often focus on grand, easily observed structures, these tiny green dots reveal that some of the most informative and extraordinary processes can occur on a smaller scale. Their rarity, compactness, and extreme activity make them indispensable to understanding galaxy formation, starburst mechanisms, chemical evolution, and the escape of ionizing radiation. They are a microcosm of cosmic extremes, a reminder that size and familiarity do not necessarily correlate with importance in the universe. Ultimately, Green Pea Galaxies inspire a sense of wonder that transcends the scientific. They are cosmic anomalies that captivate through both their appearance and their significance, tiny yet monumental in their contribution to our understanding of the universe. They prove that the universe is full of hidden marvels, where even small, obscure, and unassuming objects can illuminate the grandest questions of cosmic history. They are mysterious, rare, and striking, a reminder that the cosmos is far from fully explored, and that beauty, power, and discovery can often be found in the most unexpected places. Even in a universe that spans billions of light years, Green Pea Galaxies teach us that some of the most remarkable stories unfold in the tiniest, greenest dots, waiting patiently for us to notice their brilliance. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.